Type 1 and Type 2 errors. The conclusions reached in a hypothesis test are based on the findings from a sample. However, since samples may contain errors or biases, there are two potentially wrong decisions that may be reached. So if I could just stop there just for a quick second. The whole thing with a hypothesis test is that we're trying to make an inference about the population. So the population includes all observations. So let's just say this includes all observations. But we can't observe all these observations. So what we do is we draw a sample, and based on the sample findings, we make conclusions about the entire population itself. Now, when you do that, in other words, when you're just picking a handful of observations from the entire database, there's bound to be some errors. And that's what we're going to discuss in this module. So what kind of errors can you make when you're only using a sample in order to draw an inference about the entire population? The first error is referred to as a type 1 error. And this error occurs when we end up rejecting the null when in fact it was true. So first of all, you could see that this is an error, even if you don't know anything about hypothesis test. So let me scratch that out. Suppose we don't know anything about hypothesis test. When you reject something, when it was true, those are the only two words that I need. You rejected something that was true. Of course that's an error, right? So again, we have to sort of dumb this down to the lowest common denominator so that we can make sense of it. Let's do an illustration. Suppose that the level of significance was set equal to 10%. So this would imply that the null is given a 90% margin of error. Therefore, if the sample fell anywhere within the 90% range, the null would be accepted. However, this also means that if the sample fell within the 10% range, then the null would be rejected. So if I could just draw a little distribution here, just very quickly, if you don't mind. And let's just say this is the null range. So this would be the null range, and this would be the alternative range, right? And so what we're saying here is if the sample falls anywhere here, we would go ahead with the null. But if the sample falls here, for instance, over here, then that would be in the alternative range, so we would reject the null. But here's the problem. You just rejected the null when in fact you don't really know what the population value is. So is it possible that you rejected the null by mistake? Remember what we said before? We can't observe the population values. So how do you know that the null was wrong if you don't even know what the population value is? So do you see why this could create an error? So what's the probability that we will incorrectly reject the null when in fact it was true? Well, as I demonstrated, that would only happen if the sample fell within that 10% range. So there it is. As I explained before, the issue is that we really don't know what the true population value is. Therefore, we may have ended up rejecting the null when in fact it could have been true. And this error occurs 10% of the time. In other words, the probability of making a type 1 error is equal to that level of significance, which in our case was 10%. So what's the error? What's the other error we can make here? And again, let's see if we can dumb this down to the lowest common denominator. Well, with type 1 error, we said that, we're rejecting something when in fact it was true, right? So what's the other error? We would reverse it. We would accept something when it was false. That too sounds like an error. And that would be labeled as type 2 error. So now let's elaborate. What is type 2 error more specifically? Type 2 error occurs when we end up accepting the null when in fact it was false. However, since we don't know what the true population value really is, we have no way of knowing if the null statement is indeed false. As a result, the probability of type 2 error cannot be quantified. Let's do an illustration. Suppose that the analyst claims that future inflation will be 8%. So what would be, so this would be the null statement. This would be the null statement. And the whole thing with type 2 error is, what is the probability of accepting this statement when it's false? Well, here's a question I have for you. How would you know that her statement is false? We don't know what inflation will be in the future. So do you see the issue at the aerial view? In other words, if you look at the big picture, do you see what the issue is? So without diving into the complexities, do you see what the problem is? How do I know she's false if I don't even know what the inflation will be in the future? So there's no way I can quantify what the probability of type 2 error is. I could quantify type 1 error. It's equal to the level of significance as I illustrated before. But I can't quantify the type 2 error. And there it is. Since we don't know what the actual rate of inflation will be in the future, we cannot calculate the probability of her statement being false. So we can't quantify type 2 error. So now I present to you a summary of everything that we discussed here. And we have two scenarios. The null could either be true or it could be false. So we're assuming that, we have this knowledge of the population value, which again, in reality, that's not how it works. In reality, we don't know what the population value is. But let's just say in this case, we do know it for a fact. So there's two things that the hypothesis test could lead to. We can either reject the null or accept the null. So if the null is true and you reject it, that sounds like an error. So let's concentrate on this over here, right, ladies and gentlemen? Let's concentrate on that. Once again, if the null is true and you rejected it, that's an error. It's a type 1 error. On the other hand, if the null is true and you accepted it, that's not an error. That seems to be about right. So now let's go to the other column. What if the null is false? What are the two likely outcomes from a hypothesis test? And there it is. You may either reject the null or accept the null. Those are the only two outcomes from a hypothesis test. So if the null is false and you reject it, that sounds about the right decision. So no errors. On the other hand, if the null is false and you accepted it, that is an error. And that would be labeled as your type 2 error. So now let's make some more in-depth observation. As the level of significance increases, the acceptance range for the null will decrease. And let's just stop there for a sec. So what I've drawn here is the distribution. But in the first case, the level of significance is here. In the second case, the level of significance got wider or it increased. But now what happens is you are reducing the range. So if you look at the second scenario right there, when the level of significance increases, as we did over here, the range, the acceptance range for the null actually shrinks. And therefore, there's a greater chance you'll reject the null when in fact it was true. And that's the statement we make here. So as a result, there's a greater chance of rejecting the null even if it was true. In other words, now we're increasing the probability of making a type 1 error. And at the same time, there will be a lesser chance of accepting the null when it is indeed false. So therefore, the probability of type 2 error will decrease. So in the second scenario, because I'm reducing the acceptance range for the null, you could see how these two statements go hand in hand. Now there's a lesser chance of accepting the null when it's false, but at the same time, there's a greater chance of rejecting the null when in fact it is true, because now you've sort of narrowed its acceptance range. Note 2, as the level of significance decreases, the acceptance range for the null will increase. So now it's the opposite, ladies and gentlemen. Now it's the opposite, if I may. Just going back to this little framework that I drew, now we're going here. Because you can see in the first scenario, the one that I'm pointing towards, the level of significance is smaller, and therefore the acceptance range for the null is wider, which means, let's see what it means. There will be a lesser chance of rejecting the null when it is indeed true. Therefore, the probability of type 1 error will decrease. So when you widen the acceptance range for the null, there's a lesser chance of rejecting it. So therefore, the type 1 error is reduced. But now because using the same framework, because the acceptance range for the null is now so wide, at the same time, now there's a greater chance of accepting the null even when it's false, because you've widened the goalpost for the null so much. Therefore, there's a greater chance of making a type 2 error. Now, note 3. To reduce the probability of both errors, so whether it's type 1 or type 2, but this, I look at it as generically, to reduce errors, period, the analyst can increase sample size. In other words, the larger the sample, the more representative it will be of the underlying population, and therefore the sample will have less inherent errors. However, in the real world, increasing sample size comes at a cost. For example, if a car company wanted more accurate crash test data, then it would simply increase the number of crash tests it performed. But of course, this will result in a much higher cost. So just like most economic variables, ladies and gentlemen, it comes down to making trade-offs. Yes, it's true, if we increase sample size, we'll make less errors. But in the real world, increasing sample size can also mean higher costs.